Welcome to the History Maps podcast. Look down at your next meal. Every single bite on your plate is the product of thousands of years of human engineering, accidental genetic mutations, and, just relentless trial and error. Today, we're mapping out exactly how humanity went from foraging for survival to essentially rewriting the genetic code of the planet. This deep dive into the source material marks the beginning of our Comprehensive History of Agriculture series.
Right, and it's such a massive topic.
It really is. We are looking at the foundational shift of human civilization, which is the transition from hunter-gatherers to farmers.
Yeah, and I think it's important to start by looking at the archaeological record prior to agriculture. You see early human societies that possess this incredibly deep, localized ecological knowledge. I mean, they were not just wandering aimlessly across the landscape hoping to stumble across a berry bush.
Right, they knew exactly what they were doing.
Exactly. For hundreds of thousands of years, hunter-gatherers developed these complex, multi-step processing techniques to extract calories from wild, often toxic environments.
Like the acorn, right? I was reading about that in the sources.
Yes, the acorn is a perfect example. In its raw form, an acorn is packed with tannins.
Which makes it super bitter.
Bitter and entirely toxic to human digestion, yeah. So early foragers figured out that if they shelled the nuts, ground them into a meal using heavy stone tools, and then repeatedly washed that meal in running streams, the water would actually leach the water-soluble tannins out of the flour.
So they were essentially turning a toxic seed into a stable carbohydrate.
Precisely.
So you have these societies with this intense localized knowledge of plants and animal behavior, and they rely on that knowledge for thousands of generations. But then, roughly 11,700 years ago, the environment changes.
Right. The Pleistocene ends, the Holocene climate stabilizes, and we enter the period known as the Neolithic Revolution.
But looking at the source material, this transition from simply gathering food to actively controlling its reproduction, it wasn't some overnight discovery. How does a society actually go from harvesting wild grains to deliberately farming them?
Well, it happens through a prolonged, almost entirely unconscious evolution. If we look at the Fertile Crescent around 10,000 years before present, you had wild plant species like emmer wheat, einkorn wheat, and barley growing naturally.
Okay.
And in the wild, these grasses possess what botanists call a brittle rachees.
A brittle rachees.
Yeah. The rachees is the central stem that holds the seed head together. Now, from an evolutionary standpoint, a wild plant wants a brittle rachees because when the wind blows, the stem shatters.
Oh, I see. So it scatters the seeds across the ground to propagate the next generation.
Exactly. But occasionally, a genetic mutation occurs in a single plant, resulting in a tough, non-shattering seed head. For a wild plant, this mutation is basically a death sentence because it cannot drop its seeds.
But for a human forager?
For a human forager, that mutation is highly desirable.
Right, because the seeds stay attached to the stalk, which means when you swing a sickle through a patch of wild wheat, the mutant plants yield a handful of grain, while the normal plants just shatter and drop their seeds in the dirt.
That is the mechanical reality of the harvest. Early humans preferentially collected the non-shattering mutants simply because they were easier to gather. They carried those specific seeds back to their camps, processed them, and inevitably spilled a few along the way, or, discarded them in their refuse piles.
So without even realizing it, they were exclusively replanting the mutant seeds in the nutrient-rich soils right around their settlements.
Yeah. And over a few centuries, the localized plant population shifted entirely toward the non-shattering trait. They unconsciously altered the plant's genetic code.
It's basically a long-term, unintentional editing process. Humans were selectively keeping the typos in the plant's genetic code that happened to benefit human consumption. The plant stops dispersing its own seeds, and humans take over that job. And the data shows this wasn't just a single isolated event in the Middle East, right?
No, not at all. The archaeological data points to distinct geographical centers of independent domestication all over the globe. In the Fertile Crescent, you had wheat and barley. In East Asia, around 8,000 years ago, common millet and rice were domesticated in the Yellow and Yangtze River basins. In Mesoamerica, maize evolved from a wild grass called teosinte around 8,700 years ago alongside squash. And down in the Andes, they domesticated potatoes and quinoa.
The fact that this happened independently across completely separate regions with completely different plant species, it indicates that domestication was a scalable response to local ecologies. Yeah. It wasn't just a single idea that originated in one place and diffused outward.
Exactly. And the same principles apply to animal domestication. The sources outline very specific pathways. You have the commensal pathway, the prey pathway, and the directed pathway.
The numbers on cattle domestication really stand out in the sources. Modern cattle trace back to an initial domestication event roughly 10,500 years ago, involving a tiny bottleneck of fewer than 80 wild aurochs.
Yeah, the aurochs was a massive, highly aggressive wild bovine. I mean, capturing and keeping them alive required deliberate strategy. Animal domestication involved selecting for specific behavioral and physical traits.
Like what kind of traits?
Well, humans targeted animals with a reduced flight distance, meaning they didn't panic and run at the sight of humans. They also selected for altered reproduction cycles to ensure a steady supply of offspring, and they bred for neoteny.
Let's unpack neoteny for the listener because it explains so much about how domesticated animals look today compared to their wild ancestors.
Sure. Neoteny is the retention of juvenile physical features into adulthood. When early humans selected for docile behavior, choosing the least aggressive wolves to breed, or the calmest aurochs, they inadvertently selected for a suite of genetic traits linked to the development of the nervous system.
And that caused physical changes.
Right. Domesticated animals began to exhibit floppy ears, shorter snouts, smaller teeth, and mottled coats.
Which are traits typical of juvenile animals.
Exactly. You can see this shift beginning with sheep and goats, originating from wild ancestors in the Near East around 10,000 BCE. With the aurochs, humans shifted from hunting them in the wild to actively managing them.
And by 10,000 years ago, the bone assemblages in human settlements show a pattern of preferentially killing young males for meat while allowing females to live and reproduce, securing a localized, scalable protein source.
Right.
Now, the traditional explanation for why humans went through all this effort dates back to the oasis theory, proposed by V. Gordon Childe. The idea is that humans were forced into farming. The climate dried out, forcing people, plants, animals to cluster around a few shrinking water sources, leaving humans no choice but to manage those resources to survive. But when you look at the Natufian culture in the Levant, the timeline just doesn't line up with that theory, does it?
No, it doesn't. The archaeological evidence heavily contradicts the deterministic oasis story. The Natufians intensified their sedentism, meaning they built permanent structures and stayed in one place year-round while continuing to hunt wild game and gather wild grains.
They settled down long before they fully committed to farming.
Right. They developed heavy basalt mortars for plant processing and built stone foundations prior to full morphological domestication of plants. The data reveals a gradual, experimental adoption, not a desperate reaction to a drying climate. It was a calculated choice.
So they recognize that managing these resources requires significantly more back-breaking labor than just walking into the forest and hunting. Why make that choice?
Well, humans utilize rational agency. They recognize the potential for caloric surpluses. A field of managed wheat can be scaled up to feed far more people than the variable daily intake of foraging. They chose the reliability of scalable calories over the precariousness of the hunter-gatherer lifestyle, even if that transition brought initial nutritional stress from a less diverse diet.
And once human societies deliberately committed to these crops, they were locked in. You plant a field of wheat, you can't just pack up your camp and follow a herd of gazelles.
No, you have to stay and protect the crop.
Right, and more importantly, you need absolute control over your environment to ensure those plants don't die. Specifically, you have to control water. And that necessity leads us directly to the birth of the first great hydraulic empires in Mesopotamia, Egypt, and the Indus Valley.
Yes, the transition to a heavy reliance on agriculture necessitated massive environmental engineering. Consider the physical reality of Mesopotamia, situated between the Tigris and Euphrates rivers. The water flow there was notoriously unpredictable and violent.
Sudden floods could wash away entire settlements, or an extended dry spell could wither the crops right before harvest.
Exactly. So to manage this volatile environment, early farmers engineered the shidduch around roughly 3000 BCE. This is the crane-like water lift, utilizing a long pole on a pivot with a bucket on one end and a clay counterweight on the other.
So it allowed a single farmer to efficiently lift water from the river up into an irrigation trench.
Right, and over time, they constructed vast, intricate networks of canals and levees to divert the river water across the arid plains.
But the soil conditions in Mesopotamia changed over time because of that intense irrigation. The source material notes they heavily favored planting barley over wheat.
Yeah, that preference for barley was an agronomic necessity. The constant evaporation of irrigation water under the hot sun left trace minerals behind, causing the soils of southern Mesopotamia to become increasingly saline.
And barley is more resistant to salt.
Much more. Barley demonstrates a significantly higher resistance to soil salinity than wheat. By adapting their crop choices to the degrading soil conditions, Mesopotamian farmers achieved extraordinary yields.
We're talking seed-to-harvest ratios of 24-1, right?
In some cases, yes, it was a highly productive system.
Now look at the Nile River in Egypt. The environment there offered an entirely different set of rules. The Nile provided a highly predictable basin irrigation system.
Very predictable. The Nile cycle structured the entirety of the Egyptian agricultural and administrative system. The annual inundation, known as the Akhet, occurred with remarkable regularity from July to October.
So floodwaters gently washed over the riverbanks, completely submerging the low-lying agricultural basins.
Right, and as the water receded, it deposited a thick layer of rich, nutrient-dense silt carried down from the Ethiopian highlands. This natural annual fertilization meant Egyptian farmers could cultivate emmer wheat and barley without the constant, intense canal dredging and levee maintenance required in Mesopotamia.
And the Ebers Papyrus, dating to roughly 1550 BCE, details how Egyptian agriculture relied on complex timing based on precise lunar and solar observations to maximize these natural flood cycles.
Exactly.
Shifting over to South Asia, the Indus Valley civilization relied on the monsoon cycle, which required a massive level of water storage. They engineered advanced water management systems like the massive stone reservoirs cut into the rock at Dolavira, deep wells, and standardized brick granaries. They were also cultivating the world's earliest domesticated cotton.
Right, and the physical reality of these specific river systems directly dictated the social and political structures of the civilizations that relied on them. Well, in Egypt, the predictable floods required far less daily maintenance from the farming population. Because the agricultural fields were completely submerged and unworkable during the Akhet season, the state, specifically the pharaoh, had access to a massive, idle labor force. The state utilized this through a corvée labor system.
Let's break down corvée labor for the listener because it's a concept that appears repeatedly throughout agricultural history. It's essentially taxation, but paid in sweat rather than currency.
That is an accurate framing. The state demands a certain number of days or months of physical labor from its subjects as a form of tax. In Egypt, the state redirected the farmers during the flood season to build monumental structures, temples, and the pyramids.
So it was a highly centralized system built on the predictable abundance of the Nile.
Yes. Contrast that with Mesopotamia, where the threat of destructive floods was constant and unpredictable. Maintaining miles of levees and dredging silt from canals required continuous, intensive labor coordination.
The sheer logistical demand of organizing that labor to prevent catastrophic flooding necessitated the creation of permanent, intense bureaucratic administration. It quite literally birthed the first city-states.
Exactly.
Think about the administrative burden of operating a Mesopotamian city-state. You have a massive centralized warehouse full of surplus barley. You can't just rely on human memory to know which farmer contributed what portion or how much grain needs to be distributed to the canal diggers tomorrow. How do they actually solve that administrative nightmare? Did the physical necessity of tracking barley yields directly invent writing?
The archaeological record heavily supports that causal link. If you look at the earliest Sumerian cuneiform tablets, dating from around 3500 to 3000 BCE, they are not recording poetry or mythology.
They're accounting ledgers?
Yes. The earliest written symbols heavily featured documentation of barley, which was used both for daily sustenance and as a standard unit of exchange. The state needed to track crop yields, manage the redistribution of grain from the temple storehouses, and organize the rations for the canal maintenance crews.
So that absolute necessity to track agricultural inputs and outputs drove the development of a durable written record. Agricultural productivity and state formation are fundamentally intertwined with the origins of written language.
Precisely.
While the river valleys of the Near East and Africa relied on flood management, farmers in East Asia and the Americas faced completely different ecological challenges. They lacked these massive, predictable floodplains. They had to engineer entirely different landscapes from scratch to feed their populations. Let's examine East Asia.
Okay, so in the Yangtze River Basin, the archaeological record shows the independent emergence of wet rice cultivation, dating back to roughly 7000 BCE. This system demanded highly labor-intensive practices.
Because farmers had to artificially flood fields, right?
Yes, physically transplant individual seedlings from nurseries into the submerged soil and maintain rigorous weed control. But the return on that labor was immense caloric yields per hectare.
And a major demographic leap occurred during the Song dynasty, around the year 1012, with the introduction of champa rice from present-day Vietnam. What made champa rice so vital to the region?
Champa rice possessed a specific genetic advantage. It matured very quickly, in approximately 100 days, and it was highly drought resistant. Prior to its introduction, farmers could only manage one harvest per year.
But champa rice allowed for double cropping harvesting twice in a single year on the same plot of land.
Exactly. This effectively doubled the caloric output of southern China and triggered a massive population boom.
To support that kind of intensive agriculture, the scale of their water engineering had to be staggering.
It was. Consider the Dujiangyan system, engineered around 256 BCE by the Qin state official Li Beng. This hydraulic infrastructure diverted the Min River's flow using artificial islands and channels, notably without the use of a traditional solid dam that would block sediment and cause flooding.
And that system irrigated over 600,000 hectares across the Sichuan Basin, preventing recurrent floods and sustaining agricultural productivity for millions of people for over 2 millennia.
It's an incredible feat of engineering.
Now let's move across the globe to Mesoamerica. The civilizations there didn't have rice, and they didn't have wheat. Maize was domesticated from a wild grass called teosinte roughly 8,700 years ago. And the biological leap from a tiny grass stalk to an ear of corn is quite striking. To grow it effectively, they developed a highly specific intercropping system called the milpa, centered on what is known as the Three Sisters: corn, beans, and squash.
Right. And further south in the Valley of Mexico, the Aztecs and their predecessors engineered chinampas.
Which are artificial islands.
Yes, chinampas were artificial agricultural islands constructed directly within the shallow lakes of the region. Farmers drove stakes into the lakebed, wove reeds between them to form enclosures, and then piled up layers of nutrient-rich lake muck and decaying vegetation until the platform rose above the water level.
That's fascinating. The chinampas enabled highly intensive year-round cultivation, utilizing the continuous water supply from beneath and the constant replenishment of organic sediment to sustain exceptionally high crop yields.
And down in the Andes, they had to farm in high-altitude freezing environments.
Right. The civilizations in the Andes, such as the Tiwanaku culture, centered around Lake Titicaca. They engineered what are known as camalones, or raised fields.
Yeah, these were earthen platforms elevated above the natural terrain, separated by a network of water-filled canals. This was a brilliant adaptation to the harsh, high-altitude cold.
So the raised earthen platforms kept the crop roots above the flood-prone saturated soils during heavy rains.
Exactly. But, more importantly, the surrounding water in the canals absorbed solar heat during the intense daytime sun. At night, when temperatures plummeted toward freezing, that water slowly released its thermal mass, creating a localized microclimate that mitigated severe frost damage to the crops.
That is just brilliant. Additionally, Andean societies domesticated llamas and alpacas around 6,000 to 7,000 years ago. They utilized them primarily for their wool and as pack animals for transport over the steep terrain. But notably, they didn't use them for draft power.
Right, no clouds.
Let's focus on the Three Sisters system because it represents something much deeper than just throwing 3 different seeds into the same hole. How does this system actually function on a biological level?
The Three Sisters system demonstrates profound empirical agronomic knowledge. It is a highly intricate polycultural intercropping complex. You plant maize, beans, and squash tightly together in small mounds. The architecture of the cornstalk provides a natural, sturdy vertical trellis for the climbing bean vines, eliminating the need to construct artificial supports.
And the beans perform a critical chemical function?
Yes, their roots harbor nitrogen-fixing rhizobia bacteria. These bacteria pull atmospheric nitrogen gas from the air spaces in the soil and convert it into nitrates, a form of nitrogen that plants can absorb, actively fertilizing the soil for the corn and squash.
And finally, the broad, low-lying leaves of the squash plant provide thick ground cover. This shading suppresses competing weeds and significantly reduces moisture evaporation from the soil. It is a perfectly calibrated, self-sustaining biological engine.
It really is.
They solved the fundamental problem of soil nutrient depletion without needing a single drop of synthetic chemicals. They achieved all of this, built these massive empires without draft animals. They lacked oxen or horses, so they couldn't use plows. They relied entirely on human labor, using tools like the digging stick, and maximized efficiency through these complex intercropping methods.
The absence of large draft animals constrained the development of mechanized tillage across the Americas, compelling indigenous farmers to refine these intensive manual techniques. Yet the caloric output of systems like the chinampas and the milpa sustained substantial demographics. By 1519, the central Mexican region alone supported an estimated population of 18 to 25 million people.
This localized, intensive knowledge sustained massive populations in the Americas and Asia. But across the ocean in Europe, the struggle with heavy, unforgiving soils was birthing a vastly different, rigidly hierarchical agricultural system. We're talking about the medieval period spanning roughly the 9th to the 14th centuries.
Yes. In Europe, the dominant socioeconomic structure was the manorial system. The peasantry, or serfs, were legally tied to the land. They were obligated to cultivate the lord's domain, the land directly owned by the local lord, while also managing their own scattered strips of land within communal open fields.
And the crucial technological shift during this era was the adoption of the heavy moldboard plow, which spread across northern Europe between the 8th and 11th centuries.
Right. Prior to this, farmers used the lighter ard plow, which essentially just scratched the surface of the soil. The ard plow was sufficient for the light, sandy soils of the Mediterranean, but it could not penetrate the dense, heavy, waterlogged clay soils of northern Europe.
How exactly did the moldboard plow solve that problem?
Well, the heavy moldboard plow was a massive piece of equipment, often requiring a team of 48 oxen to pull. It featured a sharp iron coulter that cut vertically into the sod, followed by a plowshare that cut horizontally. The critical innovation was the moldboard itself.
That's a curved wooden or iron plate, right?
Yes. It physically caught the cut earth and turned it completely over. This deep tillage buried weeds, brought deeper nutrients to the surface, and created furrows that drastically improved the drainage of the heavy clay soils.
They combined that mechanical innovation with a new chemical strategy for the soil, the three-field rotation.
Right. Prior to this, European farmers used a two-field system. You plant half your land and leave the other half unplanted or fallow for an entire year so the soil can recover its nutrients.
Which means half your land is unproductive at any given time.
Exactly. The three-field rotation system divided the arable land into thirds. They planted winter grains, like wheat or rye, in the first field in the autumn. In the second field, they planted spring crops, like oats, barley, or legumes, such as peas and beans, which also helped fix some nitrogen back into the soil.
Only the third field was left fallow. This shift from leaving half the land idle to leaving only 1/3 idle effectively doubled the amount of cultivable land without requiring any new clearing.
And when you combine the heavy plow, the three-field rotation, and the milder climatic conditions of the medieval warm period from roughly 900 to 1300, Europe's population more than doubled, reaching roughly 70 to 80 million.
Despite that population growth, the open field system had severe structural limitations.
It did. The communal nature of the open field system strictly enforced uniform practices. A village decided collectively when to plant, what to plant, and when to harvest. If you were an individual serf managing your specific strip of land within that massive field, you had zero individual incentive to experiment with new crops, improve drainage, or carefully manage your soil.
You couldn't even fence off your area. And after the harvest, the village livestock grazed freely over everyone's stubble.
Right. Because the land was managed collectively and your surplus was heavily taxed by the Lord, individual innovation was stifled. This led to a long-term stagnation in productivity. Throughout the medieval period, seed-to-harvest ratios hovered around a modest 4-to-1 or 6-to-1. You plant 1 grade of wheat, you harvest 4.
But I want to challenge the traditional Western narrative here, because while European agriculture was locked in that communal stagnation, struggling for those 4-to-1 yields, the Islamic world was executing what historians now call the Islamic Green Revolution.
Yeah, the contrast is significant.
They were applying complex agronomic science and advanced water engineering to turn arid desert environments into highly productive year-round agricultural estates.
From the 8th to the 13th centuries, the Islamic world, stretching from Spain to Central Asia, rapidly adopted and expanded sophisticated agricultural technologies. They proliferated the use of quanates.
Remind the listener what a quanat is.
A quanat is a gently sloping subterranean aqueduct tapped into a groundwater source in the foothills. By transporting the water underground over long distances, they virtually eliminated the massive evaporation losses that plague open-air canals in arid climates.
They also deployed massive water wheels called norias. A prime example is the Albalafia in Cordoba, Spain, which utilized the flow of the river to turn a massive wheel, mechanically lifting water into an elevated aqueduct system.
Furthermore, in the windswept Khorasan region of Persia, They constructed early vertical axis windmills to grind grain and pump water, representing an early application of non-animal mechanization.
And they paired that engineering with a deeply scientific approach to the plants themselves.
Agronomy became a rigorous science. Scholars compiled comprehensive treatises on land management. In 12th century Seville, Ibn al-Wam wrote the Kitab al-Filaha.
This text is incredibly detailed, covering grafting techniques, precise soil types, manure mixtures, and the cultivation requirements for over 180 specific plant species.
The Islamic world acted as a massive conduit, facilitating the transfer of new cash crops from East Asia and India, such as citrus fruits, sugarcane, hard wheat, and rice, across the Mediterranean into North Africa and Al-Andalus.
How did they manage the legal and financial side of this massive infrastructure? I mean, you build a subterranean aqueduct, it requires constant maintenance.
Well, because they integrated advanced, reliable irrigation, they could support multi-cropping cycles, growing summer staples in semi-arid landscapes that previously only supported winter crops. To protect the capital investments required for this infrastructure, they utilized Waqf endowments.
Well, WAC is a charitable trust established under Islamic law, correct?
Yes. It legally protected agricultural lands, orchards, and irrigation infrastructure in perpetuity. The revenue generated by the WAC could be used to fund mosques, schools, or hospitals, but the land itself could not be subdivided, sold, or confiscated by the state. This legal framework ensured the long-term, multi-generational maintenance of complex irrigation networks without the risk of fragmentation that plagued European inheritance laws.
So these two distinct agricultural spheres, the Americas with their biological engineering and the Old World with its plows and aqueducts, they were about to crash into one another in 1492. This sparks an exchange that permanently rewrites global demographics, the Columbian Exchange.
The Columbian Exchange is arguably the most significant ecological event since the end of the Ice Age. It involved the widespread, bidirectional transfer of plants, animals, human populations, and diseases across the Atlantic.
From the New World, Europe and Asia received crops that were entirely unknown to them. Potatoes, maize, sweet potatoes, tomatoes, peanuts, and chili peppers.
In reverse, the Old World introduced wheat, rice, barley, apples, and large domesticated animals like cattle, horses, pigs, and sheep to the Americas. Tragically, the Old World also introduced devastating pathogens, including smallpox, measles, influenza, and typhus.
The impact of those diseases on the indigenous populations is almost impossible to fully grasp. We are looking at an 80 to 95% reduction in populations across the hemisphere by the mid-17th century.
The demographic collapse in the Americas was absolute. Entire societies and deeply localized agricultural knowledge bases were wiped out in a matter of decades. Yet, simultaneously, the introduction of New World crops to the Old World triggered an unprecedented population boom. The driving factor was sheer caloric superiority and adaptability.
Let's focus on the potato. Why did a tuber from the Andes become the fuel for European population growth?
The potato possesses remarkable agronomic advantages. First, it yields up to 4 times more calories per acre than traditional European broadcast grains like wheat or rye.
4 times the calories, that's huge.
It is. Second, it is highly nutritionally dense, containing complex carbohydrates, vitamin C, and potassium. Third, because the edible portion grows entirely underground, it is protected from sudden frosts, and crucially, it is protected from the trampling boots and foraging of armies, which frequently devastated above-ground grain crops during European conflicts.
You can see exactly how that caloric density altered specific nations. Look at the data for Ireland.
In Ireland, the political and economic landscape meant the peasantry had access to very little land.
Yeah.
The potato allowed subsistence farmers to subdivide those small plots of land among their children, while still generating enough calories to feed large families.
As a direct result, the Irish population surged from approximately 2 million in 1700 to over 8 million by 1841. We see a similar demographic explosion in China with the introduction of maize and the sweet potato.
Right, because these crops could be grown on dry, marginal, mountainous hillsides that were entirely unsuited for wet rice or wheat cultivation. This massive expansion of usable agricultural land contributed to China's population growing from roughly 100 million in 1500 to over 300 million by 1800.
But we have to examine the dark side of this caloric boom. While the potato fueled the rise of Europe, the economic structures surrounding it created a trap, didn't they? The mercantilist pressure to export grain forced the poorest classes into a dangerous monoculture dependency, which later resulted in catastrophic famine.
Yes. The caloric density of the potato was utilized within a specific extractive economic framework. In Ireland, the land was largely owned by absentee British landlords. The mercantilist policies dictated that the high-value agricultural outputs, wheat, beef, and dairy, were grown specifically for export to Britain to generate cash.
And the Irish tenant farmers used the small remaining patches of land to grow potatoes strictly for their own survival.
While the potato provided a massive short-term caloric influx, this absolute monoculture dependency created extreme ecological vulnerability. They relied almost entirely on a single genetic variety of potato.
So when the fungal pathogen Phytophthora infestans, known as the potato blight, arrived in the 1840s, it wiped out the entire crop. Because the economic system left them with no agricultural diversity and no capital to purchase alternative food, the result was a catastrophic famine where over 1 million people starved and millions more emigrated.
It's a stark example of the dangers of monoculture.
The caloric energy provided by these New World crops fed a growing labor force in Europe, setting the stage for an era where machines rather than human hands would take over the fields. We're entering the British agricultural revolution, spanning roughly 1700 to 1850.
The fundamental driver of the British agricultural revolution was not initially technological. It was a shift in property rights. This was driven by the Parliamentary Enclosure Acts. For centuries, English villages operated under the open field system we discussed earlier, with communal grazing lands and shared decisions.
The Enclosure Acts legally privatized those common lands, consolidating them into large, continuous, privately owned farms surrounded by hedges or fences.
And by doing that, they systematically ended the tragedy of the commons.
Right. The tragedy of the commons dictates that when a resource is shared by everyone, no individual has an incentive to maintain it, and everyone has an incentive to overexploit it. Under communal grazing, if a farmer wanted to selectively breed a larger sheep, they couldn't, because their sheep mingled and bred with everyone else's scrawny sheep on the village common.
By establishing secure, exclusive property rights through enclosure, landowners finally had the economic incentive to invest capital into long-term improvements. They could drain wetlands, build fences, and engage in systematic experimentation because they captured the full economic benefit of those improvements.
We see that experimentation immediately in livestock breeding.
Private owners engaged in intense selective breeding. Robert Bakewell, working around 1750, systematically bred his new Leicester sheep to prioritize fast growth, heavy bone structure, and high meat yields, rather than just wool.
And through controlled breeding within his enclosed pastures, the average weight of a sheep sold at the Smithfield Market in London grew from 370 pounds in 1700 to 800 pounds by 1786.
They also completely restructured how they managed the chemistry of the soil through the Norfolk four-course rotation,
which cycled 4 crops in a specific order: wheat, turnips, barley, and clover. This system completely eliminated the need for the fallow year, meaning 100% of the land was productive at all times.
Right, because the clover is a legume. Its deep roots fixed nitrogen back into the soil, acting as a biological fertilizer. The turnips provided massive amounts of winter fodder for the larger livestock herds.
Because the animals had winter food, farmers didn't have to slaughter them in the autumn. Larger, year-round herds produced significantly more manure, which was then plowed back into the fields to fertilize the wheat and barley. It was a perfectly closed loop of nutrient cycling.
And with the land consolidated and the soil optimized, the heavy machinery finally enters the picture. Mechanization accelerated rapidly as capital flowed into these private farms.
In 1701, Jethro Tull perfected the horse-drawn seed drill. Before this, farmers broadcast seeds by throwing them by hand, which left many exposed to birds or planted too shallow. The seed drill mechanically created a trench, dropped the seed at a precise depth, and covered it up,
which vastly reduced waste and allowed for weed control between the straight rows. Later, in 1834, across the Atlantic, Cyrus McCormick patented the mechanical reaper. A single farmer driving a horse-drawn reaper could cut 12 to 15 acres of standing grain in a single day, compared to the 2 acres a laborer could cut swinging a hand scythe.
Then, in 1837, John Deere introduced the self-scouring steel plow. The steel plow was specifically designed for the American Midwest. The old cast-iron plows brought over from Europe worked fine in sandy soils, but the sticky, dense, deep prairie sod of the Midwest would cling to the iron.
The farmer basically had to stop every few feet to scrape the blade clean.
The highly polished steel of Deere's plow sliced through the sod, and the sticky earth simply slid off, opening up millions of acres of virgin prairie to rapid cultivation.
The transition from muzzle to machine drastically increased output, but the plant still needed chemical inputs. In the 1840s, farmers began importing massive amounts of Peruvian guano-accumulated seabird droppings because it was incredibly rich in nitrogen and phosphate.
Then, in 1917, Henry Ford introduced the Fordson tractor, the first lightweight, mass-produced tractor, which began the process of replacing draft horses entirely. But the most consequential shift of this entire era, and perhaps in all of agricultural history, was a chemical breakthrough. The Haber-Bosch process, industrialized in 1913.
Yes, this was a massive shift.
When we talk about nitrogen, it is the fundamental building block of plant growth. We are surrounded by it. The Earth's atmosphere is roughly 78% nitrogen, but plants cannot breathe it in. They can only absorb it through their roots in the form of reactive nitrates.
For 10,000 years, agriculture was strictly limited by how much nitrogen could be naturally fixed by bacteria in the soil, or replenished by spreading animal manure. Haber-Bosch changes that permanently.
The Haber-Bosch process was a monumental scientific achievement engineered by German chemists Fritz Haber and Karl Bosch. They figured out how to synthesize ammonia directly from the nitrogen in the atmosphere.
The process involves taking atmospheric nitrogen and hydrogen gas, mixing them, and subjecting them to extreme heat, around 500 degrees Celsius, and immense pressure, roughly 200 times atmospheric pressure. They force this mixture over an iron catalyst.
Let's break down the mechanics of that. The nitrogen molecules in the air are locked together with a triple chemical bond, making them incredibly stable and useless to plants. The extreme heat, pressure, and the iron catalyst basically act as a molecular sledgehammer.
They crush the air until those triple bonds break apart and the loose nitrogen atoms bind with the hydrogen to form ammonia. That is the chemical reality of the process. Haber-Bosch allowed humanity to industrially manufacture synthetic nitrogen fertilizer on a massive global scale.
It's the equivalent of pulling bread out of thin air. By violently capturing nitrogen directly from the atmosphere in a factory, humans effectively uncoupled food production from the natural biological limits of the Earth's soil.
The scale of that intervention is difficult to overstate. Today, nearly 50% of the nitrogen atoms in the tissues of the average human body were synthetically fixed in a factory using the Haber-Bosch process.
That is notable. Without it, the Earth simply could not produce enough biomass to sustain the current global population.
Furthermore, this entire era of mechanization and synthetic fertilizer had a profound demographic consequence. As the productivity per acre and the productivity per worker skyrocketed, farms required far less human physical labor.
This massive increase in efficiency displaced millions of rural workers, pushing them out of the countryside and into the rapidly expanding urban centers. They arrived just in time to provide the dense, cheap labor force necessary to fuel the factories of the Industrial Revolution.
Exactly. Pulling nitrogen from the air was a massive leap, but by the mid-20th century, humanity faced a looming crisis.
Right. The global population was surging exponentially following World War II, and there were billions of new mouths to feed. Demographers were predicting catastrophic global famines by the 1970s. To avert that, scientists realized that simply applying more synthetic fertilizer wasn't enough. They needed an intervention at the genetic level. This kicks off the Green Revolution.
The Green Revolution, spanning roughly from the 1960s to the 1980s, centered on the intensive breeding of high-yielding varieties, or HYVs, of staple grain crops. Norman Borlaug, an American agronomist working in Mexico, identified a mechanical failure in the wheat plants.
A mechanical failure.
Yes. Traditionally, if a farmer applied heavy doses of synthetic nitrogen fertilizer to a field of wheat, the plant would grow exceptionally tall and top-heavy with grain. But the stalk was weak. In heavy winds or rain, the tall stalk would snap, and the plant would fall over into the mud and rot, a process called lodging.
So Borlaug spent years crossbreeding traditional wheat with a specific Japanese semi-dwarf variety. The goal was to fundamentally alter the architecture of the plant itself.
Exactly. Borlaug bred specific varieties of short-strawed semi-dwarf wheat. Because the stalk was short and thick, it could support massive amounts of grain without lodging when heavily fertilized. They fundamentally altered what agronomists call the harvest index.
The harvest index is the ratio of the plant's total above-ground biomass that consists of edible grain versus inedible stalk and leaves, right?
Right. The semi-dwarf varieties put all their biological energy into producing large, heavy seed heads rather than growing a tall stalk.
This wasn't just happening with wheat in Mexico. The International Rice Research Institute in the Philippines released IR8 in 1966, which was a semi-dwarf rice variety that yielded similar results.
When you paired these genetically altered seeds with heavy irrigation networks and massive applications of synthetic fertilizers, the results were staggering. These crops tripled wheat and rice yields across Latin America and Asia in a matter of years.
Completely averting the mass malfusion famines that were predicted to wipe out hundreds of millions of people.
The genetic manipulation initiated by Borlaug relied on traditional crossbreeding, which takes years of physical selection. But by the late 20th century, we entered the era of biotechnology, where scientists began editing the genome directly.
In 1994, the Flav Versov tomato became the first genetically engineered crop approved for commercial sale. Scientists identified the specific gene responsible for producing the enzyme that causes a tomato to soften and rot, and they essentially turned that gene off, extending the tomato's shelf life.
And 2 years later, in 1996, beet corn was introduced to the market.
Explain how beet corn actually works, because it sounds like science fiction. You have a plant that produces its own insecticide.
Beet stands for Bacillus thuringiensis, which is a naturally occurring soil bacterium. This bacterium produces specific crystal proteins that are highly toxic to certain insect pests, like the European corn borer, but entirely harmless to mammals and humans.
Okay, so geneticists isolated the specific gene in the bacterium that codes for that toxic protein and inserted it directly into the DNA of the corn plant.
Right, and as a result, every cell in the corn plant produces this protein. When a caterpillar takes a bite of the corn stalk, the protein binds to the receptors in the insect's gut, dissolving the gut wall and killing the pest.
This genetic intervention drastically reduced the need for farmers to spray millions of gallons of broad-spectrum chemical insecticides over their fields from airplanes.
And the technology continues to accelerate. By 2012, we see the application of CRISPR technology. CRISPR operates like molecular scissors, guided by RNA to specific locations within a plant's DNA.
Unlike older transgenic methods that inserted foreign genes from other species, CRISPR allows scientists to precisely target and edit the plant's existing genes.
Exactly. For example, researchers utilize CRISPR to edit the ARGOS8 gene in maize. By altering the promoter region of this specific gene, they increase the plant's cellular division rates specifically during times of severe water scarcity. They engineered corn that can survive and produce a yield during extreme drought stress.
Parallel to this molecular biotech, we have a revolution in the hardware: precision farming. In 1996, John Deere integrated GPS technology directly into their tractors.
Precision agriculture revolutionized resource efficiency. Historically, a farmer would drive a tractor across a 100-acre field and spray the exact same uniform amount of seed, fertilizer, and water over every square inch, regardless of the variations in the soil.
Today, farmers utilize variable rate technology, or VRT. They deploy drones equipped with multispectral cameras that map the field. These sensors measure the exact nitrogen levels in the soil and detect localized crop stress by analyzing the infrared light reflecting off the leaves, identifying problems before they are visible to the human eye.
The farmer loads this data map into the tractor's computer. As the GPS-guided tractor drives autonomously across the field with sub-inch accuracy, the VRT system adjusts the nozzles on the sprayer thousands of times per minute.
Applying a heavy dose of fertilizer to a nutrient-poor patch and turning the spray off completely over a nutrient-rich patch. I want to look at the data regarding the environmental impact because modern agricultural technology, synthetic fertilizers, and GMOs face intense public criticism. People point to them as environmental hazards.
Right, there is significant debate.
But if you look at the source material regarding the Green Resolution, it highlights a different narrative. Between 1965 and the year 2000, the exponential increase in yield per acre meant that the total global supply of calories tripled, while the total amount of land cultivated for farming increased by only 30%.
The empirical data surrounding land use is critical to understand. High-tech intensification acts as a massive environmental safeguard. If global agriculture had not adopted synthetic fertilizers, semi-dwarf varieties, and precision VRT, and instead attempted to feed a population of 8 billion people using pre-industrial extensive farming methods, the land requirements would be unimaginable.
To generate the necessary calories at medieval yield rates, humanity would have been forced to plow under nearly every remaining forest, jungle, and natural habitat on Earth.
By intensely concentrating crop production on existing arable land, the Green Revolution effectively spared millions of square miles of wild ecosystems from the plow. Furthermore, the precision application of inputs via GPS and VRT has measurably reduced cumulative, unnecessary pesticide and fertilizer runoff into local watersheds.
Looking back over this entire timeline, from a forager washing bitter acorns in a stream to a drone mapping the nitrogen levels of a drought-resistant, CRISPR-edited cornfield, it brings us to a massive historiographical debate. Considering the long arc of this deep dive, was starting this whole process a mistake?
That question forms the core of a major academic debate, largely brought into the mainstream by anthropologist Jared Diamond in his 1987 thesis. He famously labeled agriculture the worst mistake in the history of the human race.
Diamond built his argument on skeletal evidence from the archaeological record, which shows that the initial transition to farming caused severe physical declines in human health. When anthropologists measure the long bones of skeletons, they find that the average male height dropped from 5 feet 9 inches in late Ice Age hunter-gatherer populations to barely 5 feet 3 inches by 3000 BCE in early farming communities.
Furthermore, early farmers suffered from increased rates of anemia, severe enamel defects, and cavities from diets heavily reliant on starchy carbohydrates, and much higher disease loads due to living in dense, unsanitary, sedentary settlements alongside domesticated animals.
When you look at the skeletal evidence, it paints a grim picture. It sounds like a compelling argument for staying in the forest and hunting gazelles.
It clearly highlights the acute short-term biological costs of the transition, as well as the immediate introduction of rigid, unequal social hierarchies where elites hoarded the surplus. However, that analysis misses the long-term biological and technological scalability.
Hunter-gatherer societies, while perhaps individually healthier and enjoying more varied diets, were incredibly fragile on a macro level. They were strictly limited in population size.
A localized drought or a slight shift in animal migration patterns could easily wipe out an entire foraging band. They possess no mechanism to store years' worth of caloric energy. The counter-evidence to Diamond's thesis notes that as agricultural methods improved and trade networks expanded, dietary diversity increased, and human heights rebounded to pre-agricultural levels by classical antiquity.
And if you judge agriculture strictly by the cavities and the anemia of those first farmers, you completely ignore the compounding benefits of the surplus they created. Without that massive stored food surplus, the human population could never have scaled from an estimated 5 million people to over 8 billion today.
The surplus is what allowed for specialized labor. If everyone has to spend their entire day hunting or gathering food, no one has the time to invent the wheel, or write a cuneiform tablet, or study the stars.
The fields of dentistry that fix those cavities, the epidemiology that cures those diseases, the metallurgy, and the very scientific method we use to analyze those ancient skeletons would literally not exist without the foundation of the agricultural surplus.
The empirical data suggests that human beings continually utilized rational agency. Across thousands of years, they consistently chose the reliability of scalable calories over the precariousness of foraging. They absorbed the short-term nutritional stresses and the burdens of extreme physical labor in order to secure long-term demographic viability. The agricultural surplus freed a critical segment of the population from the daily requirements of subsistence, and that exact dynamic catalyzed the entirety of human technological, artistic, and social progress.
So it's about evaluating the long-term payoff.
Yes. And if we look forward based on the sources, the nature of our agricultural intervention is fundamentally shifting. For the first 10,000 years of this history, agriculture was entirely about altering the earth to suit our crops. We cleared massive forests, diverted entire river systems, mined islands of guano, and subjected the atmosphere to extreme pressure to synthesize nitrogen.
And the next era?
The next era of agriculture will be entirely about altering our crops to survive a changing earth. The plants we consume today are entirely human inventions, shaped by millennia of both unconscious selection and deliberate genetic engineering. The agriculture of tomorrow, engineered at the molecular level to withstand severe droughts and extreme resource constraints, will look as alien to us today as our vast, laser-level wheat fields would to a Pleistocene forager.
Thank you for listening, History Maps. Learn history visually.